All right. Good morning, beloved, and welcome to I guess, I guess you'd call this the beginning of the end, because it looks like that this chapter will be our last, and the it's the first unit. There's 3 units. The first unit we're going to do in one go today, and that's going to be um, uh, pretty easily done. The next 2 units, though, I'm going to split both those into two. The first part of each 2-day couplet will be in instruction and starting our reviews, and then the second day will be you'll have time to finish the reviews. That's just to spread it so that you don't freak out every day with getting farther and farther behind, and wanting to keep work to the 1 hour as much as we can. Okay, so magnets. There is a couple of YouTube's videos from Khan Academy, Introduction to Magnetism, and I'm not sure what the next one is called. They kind of basic. I think mostly you will have a sense for it already, but let's just start and see how far we can get today. So the idea of magnetism is a bit of a mystery. Um, um, the real finer parts of it are more mysterious than I'm going to make them out to be. But my understanding of magnetism is that in a non-magnetic piece of matter, or let's say a chunk of metal that's not magnetic, the metal atoms have got a lot of electrons that are on in the valence shell. Okay, they're out there, and for the most part, they don't have any real strong what you call it, directionality. So that if you were to imagine electrons in one atom, uh, if they fell to one side, so if you've got an atom that is surrounded by electrons, and he's got a neighboring atom that is also surrounded by electrons, if for some reason the electrons tended to congregate on one side, like this, then this would have an effect on the electrons on the neighbor, pushing them because of electron repulsion. It would be pushing them to the other side, and on and on and on, and that can occur. Keeping in mind that these electrons are in motion, and most of these associations are going to be very transient. So that if you were to try to diagram this in this square, imagine this is a piece of, say, iron, these directionalities would be somewhat randomized, no particular direction at all. Okay, try to think of it, whatever, whatever, whatever. Okay, and the difference is that sometimes by design or by accident in a magnetic piece, these if you imagine dividing these into somewhat areas because of interactions, localized interactions, they set up what they call domains. Now the domains can go in different directions, but if the majority of them are going in one direction, then you have a magnetic field produced. Okay, and the greater the number of these domains, so this is called a domain, the greater the number of these domains that are in the same direction, the stronger their magnetic field. Okay, so that's my understanding of things, but that's a rather simplistic one, granted. Charles Dufay came out with the laws of attraction and repulsion. And so basically there are three different scenarios. There's what's happening if you have, I'm going to draw a series of magnets here. Actually, three couplets of them. And I'm going to say in this one here, this is the north pointing direction. Notice I said north pointing. I invite you to watch the first video from Khan Academy. Because the convention is that if you have a magnet, the end that points towards our geographic North Pole is said to be the north end of the magnet. What we do know now, though, is that that's convention. The idea is that if you'd imagine the Earth having a bar magnet itself that goes from the North Pole to the South Pole, the actual magnetic, what would you call it, similarity is that Earth magnet at the North Pole would be the South Pole of the magnet. So north goes to south, north goes to south. And so what happens is that the north end, the direction of a magnetic field by convention goes from north to south. So in this case here, you would expect that this is the direction of the field. Okay, so it's like this, north to south in that direction, and as you go out it gets weaker, but it's going north to south, north to south, north to south, and likewise and as you get farther away, the effects get smaller until you get so far away that there's negligible force. Okay, now keeping this idea in mind, north going to south, I'm not going to do a lot of them. We've already got the idea that north goes to south. If I, so if I try to put two north-seeking magnets together, put the north ends together, then there's going to be repulsion. There's going to be repulsion for this way and repulsion this way. So there's repulsion here, and there's attraction here, and north goes to south, north goes to south, north goes to south, south. So there's a repulsion happening here. And the moral of the story is that always and forever, north to south. Okay? Okay? There are 4 elements. There's more than 4 elements. I think there's 5 elements that are magnetic. Iron's 1. Nickel's 1. Cobalt's 1. Gadolinium. And neodymium. And I think there might be one other, but I'm not sure. This guy is a rare earth, so he's called a rare earth magnet. Gadolinium and the other 4 aren't. They're more common than the rare earth magnet. Alnico is a mixture of 3 of these and aluminum. Aluminum is not ferromagnetic. It's not magnetic at all. So, but it's mixed in. I think I'm not sure quite why. Maybe it's a binder. I don't know. So alnico is nickel. Cobalt. Cobalt. And iron. In aluminum. Aluminum is very soft compared to any of these guys, and easily has a lower melting point and whatnot as well. Ferromagnetic, that's just a term that we use to identify an element as that they can actually have a magnetic field. So these guys, if it's ferromagnetic, can possess a magnetic field. It's not necessarily that they do, though. And so we already got those guys. Fe, the common ones anyway. And we already have determined that, we've already said that north, the South Pole, the magnet, the lines of magnetic force, or flux lines, they're called flux lines, are tighter and more, therefore stronger at the tips. Okay, are at the concentration points. As you move away, they get weaker and weaker, and so to show that, we increase the distance between them. So that means that sorry, you can't see that. This distance in here is indicates that this is stronger. This is a weaker. And if I did one more just for the heck of it, this indicates that it's weaker still. Okay, and so as you go, these would spread out. If we wanted to be diagrammatic, these would spread out over distance until the distance between them is so far that you don't notice the magnetic field. So it's not demonstrable. Okay. Lines of force. Basically, we've already covered that, but it's on my notes, so I'm going to do it anyway. But I'm so glad that I've got the colored version and you don't. well, I shouldn't say it that way. I should say, I'm so glad I have the color version. You don't. Always goes. Okay? So a solenoid is if this was we're going to talk about the right-hand rule in a second, Ampere's right-hand rule. But basically, the the solenoid has a direction. A solenoid is basically a coil of wire in which a current is flowing. Okay, and it depends on which way the current goes, where and that determines the magnetic field, which direction it has. So we can demonstrate how that is later on when we discover what the right-hand rule is. But basically, a conventional current, and we'll talk about this more in a second, but basically conventional current is given I, and that is equal to the direction that a positive charge would move. Basically, it's opposite to electron flow. This is called conventional current. Why do we do that? Well, it explains phenomena. That's all I can really say. It makes life easier, but basically, if you have conventional current flowing in this solenoid, this coil of wires, and so basically the positive is going this way, then the direction of the magnetic field is going to be this way. This is going to be the north field. Okay. So we'll come back to that later on, maybe. I think that there's somewhere there is another diagram. I'm not quite sure if it's in here or if we do this in the book. I don't know. But anyway, we can come back to that. Ampere's right-hand rule. This is really important. And Ampere's right-hand rule. This addresses current in a wire. So if this, so here we have current carrying wire here, okay, and the direction of conventional current, so this conventional current is going this way, okay, and we said that this is the in which positive charges would flow. If you point your thumb in the direction of your of the conventional current and wrap this is your right hand, and you wrap your hand around it, your fingers will point in the direction of the magnetic field. That's the point of it, okay? So this is the, it's here, is the direction of magnetic field. And of course we all know that conventional current flows opposite to the flow of electrons. Okay, electrons are going that way. Okay, there are two other things that you might that are important. Two other symbols that we're going to be looking at. Now, one is this. Sometimes you'll see it. This plus sign, or sometimes you'll see it as an X sign here, and this means that the wire is going into the page. It's going this way. Okay, so this is into the page. Okay, the other symbol that you'll see is this with the dot, and this means out of the page. Okay, now how I remember this is I used to be an archer once upon a time. So this, of course, is the tip of the arrow, and this is the fletching. The feathers are, the actual term is called fletching. Okay, and so if you were looking down from, if you're looking from this side here, what you'd see is basically this. These guys here. You're going to see the fletching, so that's pointing into the page. If you were to look at it from this side, you would see the tip coming towards you, which is that there. So it's coming out of the page. So if I was to ask you, here's a little exercise for you, and I encourage you to stop the video and to see if you can draw lines of force, magnetic force, around these two pairs. So you're going to deal with this pair first, then you're going to deal with this pair first. So pause and then come back. Okay, so using the right hand rule, so you're going to put your hand this straight, because you can see my thumb is pointing into the page, and so your lines of force are going to go this way. So this one here, we'll start by putting a line of force here just to get the sense of what's going on here, and we have a sense it's going this way here, this way here, and as it gets, as you go farther and farther away, these things increase too. So what you'd expect when you get out far enough is that these forces would interact. So if you've got two current carrying wires going in, this is what the lines of force would look like. Now, what is not intuitive, at least at this point, is what is going to happen between these guys. Well, it's going to, they're coming together, they're holding hands almost. So these guys here are going to be attracted to each other. This does not mean positive charge. This means that the current carrying wire is going into the page. So don't say, oh, Mr. Hayden, positive charge is repelled. No, that's what we're talking about, okay? These are two current carrying wires. It's a bit different. So we go over to this one here, and so we have this guy here is going to be doing the same. He's going to be going this same direction as his neighbors, like this. And on this guy, he's going to be going the opposite direction. If you keep going bigger and bigger, oh, I did this wrong. This is going this way. That's what I mean. This is going to be, this is supposed to be going this way. I've got there that arrowhead going wrong, and I've got this arrowhead going wrong too. Do I? Yeah. Switch the arrowheads. That's supposed to be going that way. That's supposed to be going that way. So this is going this way. And so what you would expect is like these guys are going against each other. They're trying to go against each other. So this is going. You're going to see a repulsion going on. Okay. Now there's two other diagrams that you're going to run into, and you have to be a bit careful about these. One of them is what happens, which direction will a compass point, because it points in the direction of the lines of force, if you put a compass underneath. So in order to indicate the compass is underneath, we can't cross those lines. So you can see that the compass is underneath, okay? So let's say the current is going in this direction. Let's say it's going that way. Well, how do you deal with that? Well, what you have to do is you have to say, okay, my thumb is going in the direction of the current, okay? So my right hand wraps around, and so the force, the magnetic force, is going underneath that way, okay? So that's the direction of that the needle will point. The other way you can see this, or the other diagram that you'll see, is this. So this is where the compass is on top of the wire, or this side of the wire. So how do you deal with that? Well, again, you put your hand in with your thumb pointing the direction of conventional current, and so this is, and you wrap your hand around the wire, so it's going to go over this way. So your compass will point in the direction of force that way. Okay, that makes sense? Fun with magnets. Okay. Now there's one other definition kind of thing on the next page. What did I do? Oh, there it is. And that is, what is an electromagnet? So basically, an electromagnet is a solenoid. We already know what a solenoid is. It's a coil of wire, okay? with a current going through it. So a solenoid is with an iron core. This produces a strong magnetic field. So I'm not good at drawing solenoids, but I'm going to give it a shot. So let's pretend that this is the magnetic core. Like so. And we have put a wire, and it is going around. I'm not good at this. And so current is going that way. And so we said before that the magnetic field, the north magnetic field, is this way. So that would be the north end of this electromagnet. This would be the south end. Okay? Okay, so quick check 7.1.1. This is just practice with what we've already done, and it's really, really straightforward. Okay? Now, I'm actually going to get you to switch videos right now. I want you to go to this site here, and I will have this below. But this is a physics demonstration of what this is here, and it's kind of like a good idea to watch it first, then come back and continue on with what we're doing here. Okay? So pause this one, go watch the other one, and come back. Okay. I'm assuming you've watched the physics demonstration, and so now you see what's going on here. So this is, again, this is invoking the right-hand rule in regards to the flow of electrons in conventional. So this is where the conventional current and flow of electrons starts to get a bit confusing. So what you have to do is this is a diagram of the right-hand rule, and so the idea in this is a different form of right-hand rule. This is the right-hand motor rule, and so in this one here, if you point your thumb in the direction that the positively charged particles would go, in other words, conventional current, positive to negative, and you put your fingers, your extended fingers, in the direction of the magnetic field, in other words, going from north to south, then the force on the beam will be in the direction of your of the top of your basically coming out of the top of your palm. Okay, so you saw that in the last video, very dramatically too. I love that video because boy, that beam responded. But basically, if you're going to use this, it's too bad I got such a big hand. But if you imagine my hand going over, conventional is going from here to here, even though we know the electrons are going in this direction. And that's why in this is the cathode ray. We're not throwing protons between. we're throwing electrons, so electrons are coming through here. But if we point our thumb in the direction of the conventional current and point our fingers in the direction of the field, then the force is downward. See, downward, and that's why the electron beam is being pushed downward. Okay? So now I hope using this and kind of like doing it yourself, using your own hand on here and thinking about the video that you just saw, that this will kind of like make a little bit more sense to what you're seeing. All right? So, that being that, we're not going to spend a lot of time on this because once we get into our questions, it'll become more apparent. This is what would you call it? The same kind of thing. It's like a CRT, cathode ray tube. We've seen this guy before, where you have voltage accelerating a particle through deflecting plates. Okay, so you have deflecting plates. Say, well, they begin about here, I guess. Deflecting plates here, and this is deflection in both directions, just like you saw in the video. Okay, and this equation is talking about the deflection. So this is the deflection here. I'm just going to highlight the deflection here in either direction. Okay, is equal to 1/2 acceleration times time squared. We get that, but you can break AT up because force is equal to mass times acceleration. So acceleration is equal to force divided by mass. Time, you can break that up into the length that it takes to go divided by the velocity, okay, squared. Okay, so that's what this is all about. So this is referring to this the velocity. Where's my green? Here's the green. How fast that is going. Okay. And so the force and the mass, those are other variables. Now, you look at this and you think, oh my goodness, do I have to play with that? And the answer is not really, because we'll find that when we start doing the equations that some of these things are kept constant, and so we don't even pay attention to them. Because they're constants, we just consider them like a 1/1, because we're comparing other things. Okay? So that's why, like on the next, if you look at the bottom of the page, I have an explanation here. Because I don't want to freak you out. The textbook goes into a little bit more explanation of this equation, but in reality, when we get right down to doing the work, just read through this. Just for the most part, problems centered around this topic are not multivariable calculations. Most questions are about the change in one of the variables, of how the change in one of the variables will change deflection if all other parameters are held constant. These are done algebraically when the remaining variables are collectively held to be constant. Okay? Now, I'm going to stop the video now because the next thing up is review 7.1. What I would like to do is I'm going to let you go work on those for the next 20 minutes, and then come back and or connect with me if you have questions, particularly in regards to question, I'm just looking at my text, question number 9. Okay, that is one of these things where you're comparing. So if you don't make it, then I will try to do a little bit of an explanation of that one next day. The rest of them basically are just qualitative questions. They're just understanding and answering what we've already done. Okay? Well, I will see you next day, and I look forward to that encounter. Bye now.